Thanks, Pierre and John, for the introduction, and to the organizers for the invitation and for me to give the possibility to give a talk. My talk is about non-local inpainting of manifold value data using finite weighted graphs. So I first want to talk about manifold value data and the problem of inpainting, then present finite weighted graphs and the infinity Laplacian we are applying to inpaint data. So manifold valued image processing. For several data, we just saw wind fields, for example. We have data that's given on a regular grid, like an image grid, but the values we have are not Euclidean, like ray-valued or color-valued images, but each pixel is a value on the manifold. This is the easiest example we had, I think, also in the first talk, or in the morning, I don't recall, where you have a height map here of Mount Vesuvius, but modulo wavelength. So it's a value on S1. That's why I already colored it in hue, because otherwise at red you would see a jump from black to white, whereas there's no jump. So that's the easiest example of phase values in each pixel. The second idea is surface normals. So we again have an elevation data set, now not modulo some wavelength. And at each data point, we compute the surface normal and use that to colorize the image. So the height is given between green and white, depending on the height in the elevation data set. And the light is computed by the surface normal. And as you can see, it looks quite noisy. So we would maybe like to denoise S2 value data, directional data. The next example is even voxel data diffusion tensors here for the complete Camino data set, or to better see it, just a slice. Then you have pixels, where each pixel is a 3x3 symmetric positive definite matrix, here visualized as the ellipsoid of the unit sphere applied to this tensor. The last example with an image is EVSD data, electron backscatter diffraction, where you measure the diffraction of an atom lattice and not only determine the orientation but also the type of crystal. And you get the orientation, which is colored, but modulo the symmetry of the atom lattice. If you have a certain material, the atoms arrange in a certain lattice, and you can't distinguish between symmetric rotations, so it's rotations modulo symmetry, that's the dynamic. And the last one's wind direction flow, or GPS, wind, we had in the last talk. With that, we have data that, the values lie in a Riemannian manifold, but we face the same problems as in classical image processing. That is, we have noisy data and want to denoise, we have missing pixels and want to inpaint, or maybe even both. And today I want to talk about inpainting and the work I did with Daniel Temring on inpainting such data. So Daniel is working on finite weighted graphs. He started with image processing, and then we joined and did that for manifold value data. So a graph, well, we have a set of nodes, that's our pixels in the future, and we have a set of edges that describe connections between these pixels. And for the future, I need that these edges are directed. So if I draw an undirected edge, think of both edges the one way and the other, but I need a distinguished start node and a distinguished end node. The start node is U, the end node is V. And we introduce weights. So if I have always both edges from 6 to 5 and from 5 to 6, then the weight function is symmetric. And I can define it on the whole space of all node tuples by introducing a weight of 0 if there's no edge. So that's finite weighted graphs. How to use them? Well, the first idea is just to model forward differences or backward differences, or the neighborhood of the 4 neighboring pixels by taking a local neighborhood, so I have edges with the same weight to all neighbors. That would be just reproducing what we know from the neighborhood of a pixel in the usual image. the local neighborhood. But I could also do something like compare patches, maybe the 4 green ones or the 4 blue ones, and then I connect the most similar patches in an image. That's quite consuming to compute, but then I would have a non-local neighborhood of a pixel to similar pixels in the image, where similar structures occur around that pixel. Or I could do something like model a surface and have data on the rabbit. I don't have an application example of manifold value data on a rabbit, but you could do that with a graph. Or you could do something like point clouds, here again with a colored point cloud where you connect to the nearest points in 3D and obtain a graph describing your surface. And then you would have a graph where each vertex has a color value. That's again not manifold value, but if you then have something like diffusion through a surface or something, then you would have something like manifold valued graph data. So basically you can present anything by a graph, and what we're then facing is not an image but a vertex function. So we have a function f that maps from the vertices v into Rm for color images, into R for gray values, or into a manifold for manifold valued data on a graph. Okay, and if I'm now missing pixels, then, well, I still might have the complete graph of neighborhoods, or only a part of the graph. But some of the vertices might miss its value. Then they're indicated like, I'm missing a color. And that's what I want to implement. And that's where the manifold value graph framework is then replacing the values I have at a vertex by manifold values. And the graph infinity Laplace is the one thing I want to generalize to the manifold value setting. That's what this talk is about. So just to get on the same slide, short notations on a manifold. We have geodesics connecting points, so it's the shortest path. And we already saw in the last talks the logarithmic and the exponential mapping into the tangent space and back. So we could choose any x, look at the tangent space, and move y to the tangent space by looking at the logarithmic map, and we get back by the exponential map. Though the logarithmic map is not globally defined, of course, because, well, I don't know how to get from the North Pole to the South Pole in the sphere. That's not unique. So the logarithm is not defined. And then what we're having is the infinity Laplacian, which is defined this way. And it was already used for inpainting in image processing by Pascal, Morel, and Sper in '98. And I will explain the algorithm they use because we use the same in the end, how to inpaint. But the question is how to generalize this one to the case where, well, here it's written in a continuous way on omega, but if I'm mapping not into the real line, but into a manifold, how to generalize this. And the idea is to generalize a characterization by Obermann from 2004. He approximates the infinity Laplace by this term. So the maximum from an environment around x, the minimum plus the maximum minus 2 times the point, which is an approximation to the infinity Laplacian. And that was used and generalized to graphs by Elmore Tass and colleagues, by these strange notations. Those are upwind and downwind gradients. This is easier to read. So here we have the weight of the edge between v and u, and those are the function values of these nodes. And the square root of those is just so that the calculations are nice. You could also omit the square root depending on the definition of your weight. But we have the minimum of these with 0, and then the maximum over all neighbors of u, all neighbors v of u is the notation, minus the maximum of all these with 0. And that's what they use for inpainting on graphs. And then I discussed with Daniel how to generalize this because, well, a minimum and a maximum doesn't make sense on a manifold. So we can't directly use that. But if we look closer at the infinity Laplacian, and a solution of the Dirichlet problem is absolutely minimizing the Lipschitz extension, which is this statement. And that was used by Obermann again to describe this as, well, we could also locally look at the discrete Lipschitz constant, which is this term, the maximum Lipschitz constant. And if we minimize that, we again get a consistent scheme to minimize the infinity Laplacian. And if we rewrite that, we get to the following. So the infinity Laplace can be written like this, where down here you have again the distance between neighboring points, which is on the graph again the weight, or the square root of the weight. And these xj prime and xy prime are actually, well, the minimum and the maximum. So imagine 3 points that maximize the Lipschitz constant in an environment around x0. But I left this place in order to add a 0. So this is like the difference from f of x0 to f of xi, and this is f of xj to f of x0. And we saw in the last talk that, well, the difference for manifold value data gets a log. And that's the idea where you can do our extension for the manifold value case. And all these distances here are the differences, the weights in the graph. With that idea, we get to the manifold valued graph infinity Laplace operator, which is quite long in name, but the idea is the same. We have down here the maximizing Lipschitz constant approximation, where the difference gets a log. So we work on a tangent plane of f of u and look for the Lipschitz maximizing tuple v1 prime, v1 star, v2 star, and then this we define as the graph infinity Laplacian. So we maximize the discrete Lipschitz constant among all neighbors and use them to define the graph infinity Laplacian. So with that, we can try to solve the graph infinity Laplacian with these boundary conditions by an explicit Euler scheme, where the step size is chosen accordingly. That's one of the things we want to investigate, how to choose that, let's say, automatically and not only by taking a good guess. But then we have just, well, an explicit Euler scheme to solve the iterations. How to do inpainting with that? So these are slides from Daniel. If we have a color image, it's easier to illustrate in a color image, and there's an area missing, then we take a graph where we take all local neighbors, the ones above, below, left, and right, and add patch-based non-local neighbors, so non-local relationships to look at the structure and the local ones to keep the connection in the image. And we look at all pixels that lie on the boundary of the unknown set. We solve the infinity Laplacian and we inpaint these here on the boundary. And we repeat that, well, then the unknown area is shrinking, 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 and shrinking. And as you can see, it's inpainting the structure. It doesn't mean that the structure was there. There might also have been a large hole somewhere in the sand, but the structure around states that, well, inpainting the structure yields the zero result. And we did the same now for manifold value data. So you repeat this solution of the solving of the infinity Laplacian until all your unknown pixels are known. And we did the same now with the just presented scheme for manifold value data. For example, on the space of symmetric 2x2 matrices, which is just ellipses, and I colored them by their anisotropy index. So blue means quite anisotropic, red means circle. And we're missing the center part. And then we could inpaint with 25 non-local neighbors determined by a patch size of 6. So I take 6 by 6 pixels and compare all patches, which gets this one, or that one if I only take 5 neighbors. And I can't reconstruct the center, so the jump in the center, because there are not enough, it's not rotation invariant, so this one doesn't count. And there are not enough similar patches for this one to reconstruct, even in that setting, flat area. Okay, so there's not enough structure in this image. We took another example, this one. That's S2 data, so in every pixel we have a small sphere and an arrow pointing in the direction. And then I colored, well, the north pole is yellowish and the south pole is blue. That's the coloring you can see. And the other is arrows pointing in certain directions. And you have actually 4 lines of jumps, this one, that one, and that one. You can't see the vertical ones, but the horizontal are slightly to be seen. And we again miss the center part a little bit more than these discontinuity lines. And for comparison, we just had the second order difference. You can use that to do first and second order total variation in painting. It looks like this. So it prefers geodesic and piecewise linear, piecewise constant and piecewise geodesic continuation, which is this. And then I did the graph infinity Laplacian computation and sent this picture to Daniel, and he asked me, did you just send me the original? I said, no, the original looks like this, but that's quite similar. So there we have enough structure and enough similar data to inpaint, such that the structure is properly inpainted. That's inpainting, that's the original. Inpainting, original. There's nearly no difference, because we have enough structure in the data to inpaint this large area. So to conclude, with graphs we can model both local and non-local features that's required for inpainting. We derived a manifold valued graph infinity Laplacian for inpainting to inpaint structured data on the manifold, which works quite fine if there's enough structure present. And the next thing is, well, it's more like a vague motivation why this works, and it works quite well. But we don't have consistency, we don't have an automatic way to choose a step size, so those are the next things we want to do. Or apply graph-based PDEs to other methods in mainly manifold valued image processing, or even derive faster schemes. We'll see what we will derive there. So those are the references. The source code is based on the MVerk toolbox and will soon be also available for you to check your own inpainting algorithms. Thank you for your attention. Thank you. Questions?
I have several questions. First is that when you choose a graph framework, why not limit domain by manifold? Is it specific to inpainting task? Yes.
So comparing to your talk, you have a map between manifolds.
Yes.
And I'm kind of discretizing the domain the data is defined on.
Yes.
And that's kind of specific for image processing, because you always have a discrete set of pixels. Or a discrete set of a point cloud of data. So my data is more like implicitly placed in a space on the domain, not in the range, on the domain. That's also interesting to look at what happens if you make the points of the graph nearer and nearer to approximate something like a manifold. So the graph should model something like a manifold, if discretized. The weights are something like the geodesic distance. And if I make the points closer and closer, more and more points, then I should get something like you do with maps between manifolds. And it would be interesting what then happens to something like this operator. I don't know. So that's more like, I can compute on a graph. I can't compute in a setting where both domain and range are continuous. So I'm discretizing the domain to work. So, yes.
Other questions from
Yeah, maybe I will come back to you.
When you say that we have enough data, can you quantify this as a function of some structure, something? So how we can quantify the enough amount of the data?
So I think that depends, on the one hand, how to choose your graph, because you can choose non-local neighbors and you should choose them such that you have enough similar patches. So maybe that's the first idea when building the graph, to stop when the patches get too unsimilar, to have a kind of cutoff in the distance, in patch distances. And in general, for a method to work, I would say that's more like heuristic. To say that I have enough structure in my image to... The sand is very structured. The first example on manifolds was not, but that's more like heuristic. I have enough structure to... I don't know whether you can... Maybe with certain information measures you can do something like that. We haven't done that. But would also be nice to know whether you can inpaint something useful as a pre-processing step to decide what to do on inpainting. Yes. So.
Another question. Will not you have problems with your definition of infinite Laplacian for your setting when image manifold is not so good? For example, if values in the neighboring vertices are not in the normal neighborhood of the value in the central vertex.
So I mean, for example, when I have a graph and the node U has a value north pole and all neighbors have the value south pole. Then I would say...
For example, some another manifold not so nice.
Yeah, so then I would say the graph is chosen the wrong way or you sampled wrong. So that's more like a problem before. You need that all logarithms are well defined to the neighbors. Otherwise you have no chance to compute this kind of inpainting. You're right. So, but if you have data that switches between north and south pole, I would always say you sampled too rough. You should increase your sampling rate to be better. So that's more, again, a problem of discretization of your data or sampling your data. But you're right. There are, of course, many problems if you have a mean manifold that's against you.
Okay, thank you.
All right, so thanks again.